Hello, could somebody confirm you can hear me?
I can hear you.
Great. All right, are there any questions before we begin? Actually, before I share my screen, let me go to the grading, talk a little bit about that. I got some grading done over the weekend. I know I got the quizzes graded, however, I have not updated the quiz 4, quiz 5, so it has the full points. I'll try and do that over the next couple of days. I got most of I got worksheet lecture 14 graded. I think I got the extra study group extra study sessions graded, except for the last one, extra study group 9 or extra study week 9. I haven't got graded, but all the others I have graded. And the labs are now graded. I think for both times, but let me check on that. Yes, the labs are graded both the first and the second time. I already told you about quiz 5 is the one I need to make it at a full point. I think that's about it. If you have any questions, let me know. I do need to grade the infectious disease research project. Let me point out that the unknown notes pages, I believe they're closing this Friday. Let me check on that. Yeah, they close June 9th. So make sure you have your unknown notes pages finished by Friday. You won't be able to get into them after Friday. A number of students asked for your last test, and then you never put up your results and conclusions for the last test. So make sure you finish your unknown notes pages. They should have the test results from the test you requested, and then the test from the first 3 that I sent out to you. So both you should have the results and the conclusions. Remember, your results are observations. The conclusion is your interpretation of that observation. So if you say the test is positive and that's all you say, then that will be a deduction because you're not saying what the results are. That the test is positive is an interpretation and it's the conclusion. So you should have both the observations and your conclusions. You should also have the species under consideration, especially near the end. In your unknown notes, you do not need to put a table identifying your unknown species. You do not have to give a paragraph discussing your species, but in your unknown report, you do need both the table giving how you identified the unknown species, and it can be a formatted figure instead of a table. Most students do a table. And you need a paragraph discussing your species, and then you should give references, at least one for where you got the information, for the information you're giving for discussing the unknown species. And for your unknown report, that is due Saturday at 11:59 p.m. this Saturday. Any questions about any of that? All right.
I had a question about the report.
Uh-huh.
There was on the unknown instruction, it says to indicate the date and the time. Do we have to indicate the time when the tests were done, like 3 p.m. or something like that? Or
No, you don't need to give the time. Actually, the time I think is written in when you automatically submit. So In the unknown notes, you don't even have to give the date, but in your report, you should give the date. Okay, you don't need to give the time. The time was something that I had in the unknown report when we had students coming into an actual lab, and I allowed students to come into my lab and then somebody else's lab at a different time. And that's why I needed the time there. Obviously, that's not something we're doing on an online class, so I do not need the time.
Sounds good. Thank you.
Okay. All right. Any other questions? Let me quickly look at this. Where am I seeing? Okay, here it is. All right. All right. If there's no further questions, let's begin. Let me get out of the grade book before I open up the, oops, what the heck is that? Uh, give me a minute here. Having trouble getting out of the grade book. There we go. Don't want to show you the grades, so I want to close that down in case I happen to show the screen. All right, let me share my screen now. Remember, your unknown notes pages is going to count as one lab, so it is worth 5 points. So if you want the 5 points, make sure you have the unknown notes pages up correctly. And like I said, Friday is the last day. You can go into your unknown notes page and make changes. And Friday is also the last day you can request a test. Although if you request a test on Friday, that test must be a test that you can get the results within 24 hours. There are a few tests that you can do that, but most of the tests take 2 days, and a few of the tests take longer than that. And so if you ask for a test at that day, I'll tell you that you're going to get the results after the assignment is due, so there's no point in doing the test. Any question about any of that? All right, you're seeing my screen, is that correct? So today is June 6th, and we're supposed to be talking about Chapter 7. Can somebody confirm, did we finish Chapter 13? Let me check on that.
Yeah, we finished with plant viruses.
Okay, great. Thank you. Chapter 7 is a lesson that I leave for the end because it's a topic that students already have a good understanding of. Controlling microbial growth is Chapter 7. We're talking about disinfectants and antiseptics, and people already have a pretty good understanding of disinfectants and antiseptics. We have talked a little bit about them throughout the term, but we're going to talk about them in greater length now. So in Chapter 7, the control of microbial growth, I'm showing you the major goals on the rough outline. Know the terms. Be able to discuss the factors that influence microbial death rates. 3, be able to discuss the 3 main ways in which antimicrobial agents kill or inhibit cells. 4, understand the various types of disinfectants and how they work. And 5, understand the relative resistance of the major microbial groups to antimicrobial agents. Any questions about what we're going to cover? All right, let me blow this up. So here we're looking at the rate of microbial death. Boy, I can't get that. There it goes. And bacterial populations die at a constant logarithmic rate when they are heated or treated with antimicrobial chemicals. So when we expose microbes to an agent, if you're starting with 1 million, over 1 unit of time, this is saying a minute, but it's 1 unit, about 90% will die. So instead of 1 million, we'll now have 100,000. At 2 minutes, instead of 1 million, we'll now have 10,000. At 3 minutes, instead of 1 million, we'll now have 1,000. And that means to kill off the entire population of microbes, you'll need to leave the agent on the microbes for greater than 6 minutes, because at 6 minutes, you'll still have 1 bacteria left out of 1 million. Any question about any of that? When we look at this, the log of the number of microbe survivors, and then the time, which is a regular scale, when we're saying that cells die at a constant logarithmic rate, it means that when you're starting with 1 million over 1 unit of time, you then go down 90%. Over 2 units of time, you go down, what is that, 99%? Come on, mouse, you died. So it's a straight linear death rate. Okay. If you were to graph this with a regular arithmetic scale of the number of cells, it's not dying at a constant logarithmic rate. It's very quick and then starts plateauing off. Any question about that? This is a very complicated equation. That's a very simple equation, y equals mx plus b. When we're talking about microbial death, you should realize that the effectiveness of the antimicrobial treatment depends on a number of factors. The number of microbes present at the beginning is an important factor in when the microbes will die. The more microbes you have, the longer you need to treat the microbes to kill them all off. And that would be like if you're starting with 1 million cells, you need at least 6 minutes to drop them to 1 cell. When you're starting with 1,000 cells, then you only need 3 minutes to drop them to 1 cell. The environmental influence can affect the microbial death rate. For example, the presence of organic material will affect the death rate. When we're dealing with a hospital specimen, you're almost always going to have organic matter around the microbes. And this applies to temperature as well as just time of exposure. For example, if you're treating the microbes with bleach and there is organic matter around, the bleach will not be as effective on the microbes because of their organic matter. Bleach and some other antimicrobial agents are actually inactivated by the organic matter. The presence of a biofilm will affect the microbial death rate. Generally speaking, cells having a biofilm will be much harder to kill and will require much longer treatment than the same cells without a biofilm. Any question about that? We'll talk a little bit more about biofilms later, but the biofilm makes the cells, at least all of them, much harder to kill. And it's partly because of the film itself. And then the biofilm puts some cells in the biofilm in stasis or hibernation. And when they're not actively growing, they're much harder to kill. The time of exposure also affects the microbial death rate. So you get more killing with longer times of exposure to the antimicrobial agent. For some microbes, they have characteristics which prevent the death from happening, in which case you need much, much longer times of exposure. The main agent I'm going to talk about is endospores. If endospores are present, the time of exposure needs to be much longer if the agent has any hope of killing off all the agents. Actually, many antimicrobial agents are not going to be effective on killing endospores. And that's just because endospores are so resistant to the agents. Like bleach cannot kill some endospores, meaning some endospores of some species. It can kill some species having endospores, but some species it cannot. So bleach would not be effective for killing off all endospores. And most antimicrobial agents will have trouble killing endospores. There's only a few antimicrobial agents which will be effective at killing endospores. And we'll talk a little bit more about those agents later. And that's coming to the microbial characteristics, and we'll discuss this at the end of this lecture. Certain microbes have certain characteristics which affect the microbial death rate. Any question about any of that? All right. So know some of the terms of this chapter. I think you already know sterilization, the destruction or removal of all forms of microbial life, including endospores. This may, when we say something is sterilized, it may not include prions. Prions are really difficult to eliminate. They're not exactly alive, and we'll talk. Actually, we've already talked about prions. I didn't discuss why prions are so difficult to eliminate. To eliminate prions, you need to incinerate the material like 1,000 degrees Fahrenheit. And why that protein is so difficult to destroy or disrupt, nobody's quite ever answered it. Okay. We don't really know, but prions are very difficult to eliminate. The exception is, and this is more experimental, like with surgical instruments, they'll treat them with proteinases, and then the proteinases will degrade the prion protein, in which case it's no longer a prion. And that's about the only good way you can sterilize surgical instruments for prions. Obviously, what you do is you'd sterilize them for bacteria and endospores first, probably by autoclaving, but autoclaving would not kill the prion, which isn't quite alive, would not destroy the prion. And then the surgical instruments, you could either incinerate them at 1,000 degrees Fahrenheit, that would destroy the surgical instruments, or you could treat them with proteinases. Commercial sterilization is sufficient heat or treatment to kill endospores of Clostridium botulinum, and it's used for canned food. Disinfection is destruction of vegetative pathogens, like when we disinfect a toilet. That does not necessarily kill endospores. Usually it does not. Antisepsis is the destruction of vegetative pathogens on living tissue. Generally, an antiseptic is less caustic and less, what am I saying? Less harmful on the skin than a disinfectant. However, the same chemical could be used as a disinfectant. For example, if someone were to treat their toilet with bleach, bleach would be a disinfectant. However, if that same person were to treat their cat, meaning their cat has a wound and they treat the cat wound with bleach, they would be using the bleach now as an antiseptic, even though it's the same chemical. Any question about any of that? Degerming is the removal of microbes from a limited area, such as the degerming of the skin site where someone's going to give a needle puncture. Degerming does not sterilize the skin. It doesn't even really disinfect the skin. It just reduces the number of microbes in the region. And alcohol is a frequent degerming agent. It's not very strong, so we don't use it as a disinfectant, but we do use it as a degerming agent. Sanitization is the treatment to lower microbial counts on eating and drinking utensils to safe public health levels. So when you sanitize your plate, you're making it safe to eat on it. And that really only happens in the, what do you call it, in industry and business. In the home, we don't really sanitize the dishes, we just wash them. Any question about any of that? All right, some terms. I've got two here. Let me move that. Oops. Got to remove that. That must have been from last term. A biocide or a germicide is a substance that kills microbes. Biocides and germicides do not usually kill endospores. We have specific types of biocides. A bactericide is an agent that kills bacteria. A fungicide is an agent that kills fungus. A viricide is an agent that inactivates a virus. Any question about any of that? A biocide, like I said, is an agent that kills the microbe. Bacteriostasis is where you treat the microbe with an agent that inhibits the growth of the microbe. Once you remove the bacteriostatic agent, growth may resume. So a bacteriostatic antibiotic does not kill the bacteria. It just prevents the bacteria from growing. And off the top of my head, I do not know of any antibiotics which are bacteriostatic. Does anybody know an antibiotic which is bacteriostatic? There is a sulfur drug that inhibits the growth of bacteria, and that would be a bacteriostatic agent. It does not kill the agent. Now, I don't know if all sulfur drugs act that way or not, but there's at least one that is bacteriostatic. Some terms. Sepsis refers to microbial contamination. Asepsis is the absence of contaminated, unwanted organisms. Aseptic techniques are important in surgery to minimize contamination from the instruments, the operating personnel, the patient, and the air. You've learned aseptic technique now in microbiology. When you go into the clinical environment, try and remember to use your aseptic technique. So antimicrobial agents kill or inhibit the growth of microbes by three different ways. The agent may alter the membrane permeability, like polymyxin B damages the plasma membrane, causing a hole in the cell membrane, causing the cytoplasm to leak out, which will kill the cell. Any question about any of that? Anyways, that's one of the three ways that an antimicrobial agent can kill or inhibit the microbe, by altering the membrane permeability. You can also damage intracellular proteins. You damage the proteins, the cell can't function, and that will lead to the microbe dying. You can denature proteins like enzymes by targeting the disulfide bridges. And this is actually the way alcohol, this is one of the ways that alcohol damages microbes. It damages intracellular proteins. Alcohol also tends to dissolve the cell membrane, so alcohol maybe wasn't the best choice for there. But tetracycline is an antibiotic which actually stops protein synthesis, and so that would kill the cells. The third way is an antimicrobial agent can kill cells is to directly damage the nucleic acid. This will result in mutation and will often result in cell death. And this is the way X-rays, even UV light, damages nucleic acid. Any question about the three ways that a microbial agent can act? All right, there are different methods of obtaining microbial control. We're going to talk about the physical methods for controlling microbial growth, and then later we'll talk about some chemical methods for controlling microbial growth. We can control microbes by applying heat, by sending the microbes through a filter, by putting the microbes in a low temperature. This may not kill the microbes. Not most microbes, about 50% of bacteria can survive freezing and then thawing, but it will prevent the microbes from growing if you put it in low enough temperature. Okay, high pressure can kill microbes. Desiccation can kill microbes or prevent their growth. Osmotic pressure can kill microbes or prevent their growth. And then radiation, the last physical method for controlling microbial growth. Any questions about any of that? If not, let's talk a little bit more about heat. All methods of heating kill microorganisms by denaturing proteins and, of course, enzymes. Though if you're flaming the microbe or incinerating the microbe, in addition to denaturing the proteins, you actually turn the cells into char. And that's just because it's so high. The heat is so high. Wet heat is one way of using heat. The other is dry heat. Wet heat includes boiling and autoclaving and steaming. Dry heat includes baking, flaming, and incineration. At the same temperature of heat, wet heat is more effective at killing cells than dry heat. And I've got that shown in a little bit. Moist heat denatures, coagulates proteins and enzymes. That's actually how we cook an egg. We heat it up, and it coagulates the albumin, changing the liquid egg white of the egg into the solid egg white of the cooked egg. Boiling liquid or flowing steam kills vegetative bacterial pathogens. It also inactivates most viruses, kills fungi and fungal spores. Although you may need 10 minutes, although oftentimes it's much faster, like E. coli, you just need to bring the solution up to 100 degrees, and then you can just drop the heat or stop the heating, and that will kill E. coli. So you don't need 10 minutes, but some organisms require 10 minutes to kill. Endospores and some viruses take much longer to destroy by heat. Some can survive greater than 20 hours in boiling water. As I stated, endospores are very difficult to kill. They can be killed by heat, but it's a very long time of exposure. So reliable sterilization by moist heat requires temperatures above boiling. And how is that achieved? We use a pressure cooker, which is actually, we call it an autoclave, a giant pressure cooker. And you stick the solution or the agar in the autoclave, turn it on. It will run for 15 minutes, shown right there, at 121 degrees Celsius, under 15 pounds per square inch. And the temperature and the pressure will kill all microbes, including endospores. If you're applying steam to the microbe has to be directly treated with the steam, meaning steam only really sterilizes the surface of an object. If you have something internal, like let's say you have a rubber duck and you're sterilizing it with steam, which that would probably melt the rubber duck, but you get the point. Something that's inside the rubber duck, the bacteria inside the rubber duck, would not be sterilized. Autoclaving is very effective, and that's why we use it in the lab. Then when we give our students media or a test tube, we can be fairly certain that it's sterile because it's been autoclaved. Any question about any of that? Let's talk a little bit more about pasteurization. I believe this is the second or third time we've talked about pasteurization. That's something that Louis Pasteur invented. It reduces the number of spoilage organisms and tends to kill, tends to kill all the pathogens, but it does not kill all organisms. And that's why pasteurized substances do have a shelf life. Like when you buy your pasteurized milk, you do have to consume it within a given length of time because it does have microbes in it, and those microbes can grow and then cause the milk to spoil. But the pasteurization removes a number of the organisms which cause the milk to spoil and kills all pathogens. It allows the milk to be safe because there's no pathogens in it. And then it allows the shelf life to be longer because the majority of bacteria are killed. It's just not all of them are killed. Pasteurization is a mild heating sufficient to kill organisms that cause spoilage. The mechanism is denaturation of proteins and enzymes. It does not kill thermoduric organisms. These are heat-resistant organisms, and they do survive pasteurization. There's two pasteurization techniques where you apply the pasteurization at 63 degrees Celsius for 30 minutes. And then the second is where you bring the temperature up to 72 degrees Celsius and you only hold it at that for 15 seconds. Most pasteurized milk uses the second pasteurization technique. There's also milk which is sterilized because we heat it for 140 degrees Celsius. It's only heated for 1 second at that temperature, and we call that ultra high temperature milk. This milk does not require refrigeration till it's open because the milk is sterilized when it's treated to 140 degrees Celsius. So ultra high temperature milk is not pasteurized milk. It's actually sterilized milk. And if you ever see a carton of liquid milk at room temperature in the store, it's most likely ultra high temperature milk. The only other exception if it's radiation treated milk, in which case, instead of the ultra high temperature killing the bacteria, the radiation may kill the bacteria. Any question about any of that? All right, this picture is showing you that dry heat is not as effective as liquid heat on killing microbes. The cat has climbed into the oven because it liked the warmth of the oven. Obviously, this is not killing the cat. And I think you all know this. Whenever we take something out of the oven, even though the oven is at cooking temperature, we stick our hands in, and it's true we have pot holders on. That's because we grab the pot and then bring it out, and the pot itself will be too hot to handle. But we can stick our arm and our hands into the oven for brief periods of time. You couldn't leave them there for minutes, But if you stick them in just for a few seconds, you're fine. And the point is, you can do that with dry heat, but if you had steam at the same temperature as the oven, you could not stick your hand through steam without getting a burn. My point is that wet heat is more efficient at killing and also quicker at killing than dry heat. Dry heat sterilizes and it kills by oxidation. Here we're looking at baking, although we're not baking the cat. The cat just climbed in the oven. And how you sterilize by baking is you place the object you want sterilized in the oven at 170 degrees Celsius for 2 hours. If you remember, for wet heat, you place it in the autoclave for only 15 minutes, and the autoclave will destroy endospores. The baking may not destroy endospores. You can also use dry heat by flaming an object or by incinerating, and these are very high temperatures, and that's why it's sterilizing the object. Any question about any of that? All right. We can also use microbial control by filtration. Filtration removes the microbes from liquids and gases. Can't be used on a solid, but it can be used on a liquid or gas. And you just send the liquid or gas through the filter, and then the material on this side of the filter is sterilized. There's no cells in it. What happens is the liquid has to go through a pore, and the size of the pore is smaller than the size of the bacteria. Filtration is often used for sterilizing liquids, especially liquids that would be altered by heating or damaged by heating. Some examples include some juices are filtered. Actually, I don't know of an example of a juice that's filtered, but some juices are filtered. Coors beer is filtered. Vaccines are also filtered. Milk is usually not filtered because the fat and the protein in milk will clog the pores, and then you can't filter the rest of the milk. Any question about filtration? Low temperature can be used to control microbial growth, and what it does is inhibits microbial growth. It does not kill many bacteria. Probably most bacteria are not killed by freezing. Refrigeration itself inhibits microbial growth, but it doesn't inhibit all microbial growth. Refrigeration, 0 degrees Celsius to 7 degrees Celsius, slows the metabolic rate of many microbes, probably most microbes, but there are some organisms which can grow at this temperature, and they will eventually grow and then cause food spoilage. And that's why food you have in the refrigerator longer than 1 week should be thrown out. And that is the cold-loving organisms can grow in the refrigerator. Another advantage for refrigeration is it prevents the synthesis of toxins, like by Staphylococcus aureus, which will not grow at refrigeration temperatures. All right, I've already talked about there are some microbes which can grow at refrigeration temperature, the psychotrophs, and within about a week, there will be too many of the psychotrophs in the food for this food to be safely eaten. So after a week, most food in the refrigerator should be thrown away. Freezing stops metabolic activity. It does not necessarily kill the microbe. And when I'm talking about freezing, I'm talking about slow freezing. That's a home freezer. The good news is slow freezing, or your freezing in your home freezer, does kill all parasitic species. So any eukaryote that has a parasite, if you freeze the object, you will kill the parasites. And if you're worried about like pork having a worm in it, like trichinosis, you can freeze the pork, and that will kill the parasitic worm, the eggs. How that kills is the ice crystals form in the freezer, and as they form, they grow, and they will actually kill some bacteria cell, and then all parasitic eukaryotic cells. So all eukaryotes will be killed if you freeze it, slow freezing, and parasites. That is not quick freezing. Quick freezing would be like putting something in liquid nitrogen. You might have done them making ice cream by putting the liquid ice cream into the liquid nitrogen, and it quickly freezes it. That does not give the ice enough time for the ice to form crystals, and so that will not kill bacteria and eukaryotic species. Any questions about any of that? High pressure is another way that we can kill microbes. High pressure transfers the pressure evenly throughout a liquid, killing vegetative bacterial cells. It does not kill endospores, but there are some proteins and carbohydrates which will be altered, and that will kill a vegetative bacteria cell. We use high pressure to preserve the color, the flavor, and the nutrient value, especially of juices, which heating would usually change the color, the flavor, and the nutrient value of the juice. So many of the juices in America are pressurized. They're under pressure when they're sterilized. Although, like I said, high pressure does not kill endospores. Here's a little joke. We have a little baby coal, and then the mama coal, and the mama coal says, "Your dad's been under a lot of pressure lately." Dad was changed into a diamond, it used to be a coal, by the pressure. Desiccation and osmotic pressure can be used to control microbial growth. Desiccation is the drying. It prevents microbial metabolism. However, cells, especially endospore, can remain viable for years. Mycobacterium, which has mycolic acid in the cell wall, can resist desiccation for a couple of months. Not as good as an endospore, but it can resist desiccation at least for months. The resistance to desiccation varies by species. Some species are very sensitive to desiccation, and they die very easily. E. coli is an example. Osmotic pressure can be used to control microbial growth. And I think you all know this. We make some foods having high salt or high sugar, and then if the bacteria falls into the food, the water leaves the bacteria, causing plasmolysis, where the plasma membrane pulls away from the cell wall. And that can either kill cells or prevent them from growing. An example of osmotic pressure is molasses. It can be kept at room temperature because of the high sugar content. If anything falls into it, it's going to go under plasmolysis and will either die or not grow. And that's why you can keep the bottle of molasses in your cupboard at room temperature for years. My mother had a bottle of molasses, we figured, for about 30 years, before she finally said, I'm going to throw this away. And at 20 years, I actually made molasses candy for my father, and he ate it, and it obviously wasn't toxic, even though it was 20 years old. And it certainly had bacteria falling into the bottle whenever it was open. Any question about any of that? Some examples of desiccation is when we dry fruit, such as figs or vegetables, and then keep them on, like if you remember dried apples. Osmotic pressure being used to keep food safe. Obviously, molasses and honey are an example. High sugar content prevents other microbes from growing. Another thing would be we do this with meat and fish. We add high salt concentration, and then the bacteria can't grow, at least well, in the meat or the fish. All right. Let's move on to radiation, the physical method for controlling microbes. Radiation damages cells in two ways. There's ionizing radiation and non-ionizing radiation. Remember, non-ionizing radiation is essentially UV light. Ionizing radiation is a spectrum of the the electromagnetic spectrum, and it has high energy. Let me see if I can blow this up so I see it better. Come on. It's bactericidal, has high energy and low wavelength. Examples of ionizing radiation include X-rays, gamma rays, and electron beams. Short wavelengths. When this energy hits a molecule, it will give the molecule enough energy, and the energy will be absorbed by electron, that electron will actually escape the atom, creating an ion in the either atom or molecule. And it's an ion because the electron has left the atom or molecule. And so the atom or molecule will have a positive charge. So ionizing radiation can ionize molecules of water, producing ions, which can then react with organic molecules, especially DNA, damaging the DNA. We use ionizing radiation to sterilize certain food, pharmaceuticals, and medical supplies. If any of you have ever bought backpackers food, it's usually sterilized, assuming it's got water in it, with ionizing radiation. And that's why the food doesn't spoil. Another way you can get backpackers food is where the food is desiccated, and then you have to add the water to make the food edible. Non-ionizing radiation is UV light. That's the only form of non-ionizing radiation which damages cells. UV light, when it hits the DNA, will make two thymines, which are next to each other, bind to each other with two covalent bonds. And we call this a thymine dimer, created by the UV light hitting two thymines next to each other. And then these thymine dimers will not hydrogen bind with their A or adenine in the other strand of DNA. This thymine dimer will cause a bubble in the DNA right here. And this bubble and the thymine dimer will prevent the DNA from replicating the DNA past this point. It will also stop transcription. Any questions about non-ionizing radiation? Microwave radiation is not particularly antimicrobial, meaning microwaves do not specifically kill microbes. However, when we microwave food or some other agent, the microwaves tend to heat the food, and then the elevated temperature of the food may cause the bacteria to die. Any question about that? So microwave radiation is not non-ionizing radiation. The microwave is not particularly antimicrobial, but like I said, microwaves, when we heat our food, it tends to heat up the food, and then the heat can kill the microbes. All right, this table is giving you some the summary of the different methods of microbial control. Let me blow this up so I can see it better. We talked about moist heat, boiling or flowing steam, and autoclaving, and it's more effective at killing than dry heat, at least at the same temperature. Pasteurization is also considered a moist heat, which doesn't really sterilize or anything. It just reduces the bacteria number, and that's just to increase the shelf life and then make the food safe to eat. A dry heat can be direct flaming, incineration, or hot air sterilization like baking. And in the very high temperatures, you turn the cells into ashes or char, and then the hot air baking tends to oxidize. Filtration can separate out the microbe from liquids or gases, making the liquid or gas sterile. Refrigeration and deep freezing tends to not kill cells, or at least most cells, directly, but it prevents their growth. We didn't talk about lyophilization, so I won't talk about that. High pressure, something we use on fruit juices, preserves the color and flavors and nutrient, and it kills vegetative bacteria, but it does not kill endospores. Desiccation stops metabolism. It doesn't necessarily kill the cell, depending on how sensitive the cell is to desiccation. Like I said, endospores could survive for millennia in desiccated food. Osmotic pressure is similar to desiccation, where you have plasmolysis occurring, and that's because the bacteria, like when it falls into the molasses, the water in the bacteria will leave the bacteria and move into the molasses, causing the cell to either die or certainly not grow. Radiation, like I said, we have two types: ionizing radiation causing ions, and non-ionizing radiation. This is UV light causing UV dimers in the DNA. All right, that's enough for the physical methods of microbial control. Are there any questions about the physical methods for microbial control? If not, let's talk about chemical methods for microbial control. There are actually very few chemical agents which achieve sterility. Most antimicrobial chemical agents only decrease microbial numbers to safe levels, and most also only remove vegetative forms of the bacteria. They do not remove endospores. They do not kill endospores. Disinfection refers to the destruction of vegetative pathogens. There are a number of factors related to effective disinfection: the concentration of the disinfectant, the time you apply the disinfectant, the pH at the time of disinfection, and the presence of organic matter. Generally, the more concentrated the disinfectant, the longer the time the disinfectant is applied, and the more acidic the pH is, the better the disinfectant will destroy vegetative pathogens. The presence of organic matter, on the other hand, will tend to make the disinfection less effective. And there are some disinfectants which are particularly inactivated by organic matter. And one to call to mind is bleach. Organic matter inactivates bleach. There are different types of disinfectants. We're not really going to talk about them. Phenol was the first disinfectant that Joseph Lister came up with, and he actually treated his surgical patients with phenol because it was the best disinfectant he could find. Phenol is not particularly a good disinfectant today. We have disinfective agents which are like around 1,000 in their phenol coefficient, which is how strong the disinfectant is. And phenol only has a phenol coefficient of 1. Joseph Lister used phenol to define the phenol coefficient because when he was looking, phenol was the strongest disinfectant he could find. There's biogonides, halogen. Let me just briefly talk about halogens. There's 2 that people frequently use. Bleach is a halogen, and then iodine, like tincture of iodine, is a halogen. Alcohol is a disinfectant, but it's not a very strong disinfectant. And we usually call this a degerming agent because alcohol is not particularly good at disinfecting an agent or a surface. Heavy metals can be used as a disinfectant. Surfactants can be used as a disinfectant. And this would be something like in the hospitals to treat surfaces. I used to know a surfactant, and I'm just drawing a blank on what that is. Chemical food preservatives could be a disinfectant. Like nitrates are added oftentimes to meat, like sausage or hot dogs or bacon. And that's a food preservative that prevents bacteria from growing and then contaminating the hot dog or the bacon. There are certain antibiotics that can be used as disinfectants, and these are added to food products to keep the food from spoiling. We're not really going to talk about that, but most of the antibiotics that are added to foods tend to be added to cheeses, and that's just to keep certain bacteria from growing in the cheese and then spoiling the cheese. Aldehydes, another disinfectant. Gaseous chemosterilizers, a very effective disinfectant. The trouble is gaseous chemosterilizers like ethylene gas is very toxic to humans. And then peroxygens or other oxidizing agents like hydrogen peroxide is another disinfectant. I'll talk briefly about this one because this is one of the disinfectants that actually does kill endospores. Endospores are very sensitive to oxidizing agents. They don't like oxygen, and if you oxidize them, you tend to kill the endospores. So hydrogen peroxide, which can be found in most people's houses, is an excellent disinfectant because it can kill endospores. Any question about any of that? All right, this is looking at the table of the chemical agent. You don't need to know the mechanism of action, and then the preferred use. I'm not even going to discuss it, but you can take a look at it. When we're comparing the effectiveness of various antiseptics, you should realize that different antiseptics have different effectiveness. Soap and water is not very effective at killing bacteria. as you can see, for 100 seconds or maybe 120 seconds, you're only killing about 10% of the bacteria. So soap and water is not a very strong disinfectant. However, a tincture of iodine is a much stronger antiseptic, and it kills most bacteria within 80 seconds. And usually when we apply tincture of iodine, like they used to use this for surgery, they would just wipe it on the patient's skin, and then they would just leave it on the patient's skin because it didn't irritate the skin. And so it'd be much longer application than 80 seconds. And then the good news is it tinted the skin so the surgeon knew where he could cut and not have an infection, and someplace that didn't have the color of the tincture of iodine, the surgeon knew, I can't cut here because it'll become infected. Actually, tincture of iodine is not used very often anymore in the hospitals. They have other agents which are even more effective than tincture of iodine in working as an antiseptic. All right, any question about any of this? If you remember, we had a question very early in this class, I think it was in the lab, where we were washing your hands, and you noticed that after somebody washed their hands, there were bacteria still on their hands. And this is telling you the reason why. Usually when you wash your hands, you're only washing for about 30 seconds. And so you're actually killing less than 10% of the bacteria when you wash your hands. And the reason is soap and water are just a very weak antiseptic agent. Soap and water, the best reason for using them is you simply get rid of the grime. And when you're washing, you don't necessarily kill the bacteria, but you actually wash away much of the bacteria on your skin or your hands. But you certainly don't wash away all of them, and you don't kill all of them either. In fact, you kill very few of the cells on your hands when you wash with soap and water. All right, let's talk about some of the microbial characteristics and how it plays a role in microbial control. This is a simplified hierarchy of the relative resistance of the major microbial groups to chemical biocides. You should realize that specific agents may act differently with specific species. So let me blow this up. The thing that is most resistant to all antimicrobial agents are prions. Prions are very difficult to kill. You need to bring them to 1,000 degrees Fahrenheit, or maybe it's 1,000 degrees Celsius, some very hot temperature, and essentially turn the living matter into char. And it's really a good question. Why does a prion resist temperatures less than that? And I don't have an answer. Nobody does. There is one way you can remove prions, and it's sort of an experimental way, and you can treat them with a proteinase, and the proteinase tends to digest the prion protein, destroying it. Endospores are the next most resistant thing of bacteria to chemical microbial agents. Mycobacteria is the third most resistant. Mycobacteria have a cell wall with a lot of mycolic acid. It's very difficult for a chemical agent to get through the mycolic acid. If it's a water-soluble chemical, it's not going to get through the mycolic acid of the mycobacteria, and it may not kill the mycobacteria. The cystic protozoa, the next most resistant thing. Vegetative protozoa, the next most resistant. Gram-negative bacteria is about midway in our resistance. What's most resistant and least resistant? The gram-negative outer membrane can protect the bacteria to many, but not all, antimicrobial chemicals. So they are more resistant than a gram-positive bacteria. And then fungi and most fungal spores, a little more sensitive than the gram-negative. Viruses without an envelope come down here. So they're getting to be fairly sensitive. And then the gram-positive bacteria, that's the most sensitive bacteria to most chemical agents. And then viruses with lipid envelopes are the most sensitive to chemical agents. The reason is if you destroy the lipid envelope, or you destroy the protein coat, or you damage the DNA of the virus, you then will destroy the virus. And so viruses with a lipid are more sensitive to chemical antimicrobial agents than a virus without an envelope. Any question about any of that? All right, I talked about that. I pretty much mentioned this, that the chemical agent has to go through the porins in the gram-negative bacteria before the chemical agent can damage the bacteria. And if it can't get through the outer membrane of the gram-negative cell, it can't damage the bacteria. And that's why gram-negatives are more resistant than gram-positives. All right. There's very few biocides that'll work on endospores. And I did mention that there was one that is actually very effective at killing endospores. And that is the oxidizing agents such as hydrogen peroxide. Very good at killing endospores. All right, I talked about that. I mentioned about prions. How we remove prions has not fully been solved yet, but at least with surgical instruments, they will treat them with proteinase. And that's a mad cow. I assume this cow is either dead or dying from mad cow disease. All right, let me go back one and then point out something. See how the mycobacteria are very sensitive, are very resistant, to most antimicrobial agents? It's because of mycolic acid in the cell wall. There is one antimicrobial agent which is very good at killing mycobacteria. And it is a antimicrobial agent that we've talked about previously, and we said it was a very weak antimicrobial agent. It's so weak we call it more a degerming agent than a bactericide, and that is alcohol. Alcohol is not particularly good at killing bacteria, but alcohol is good at getting through the mycolic acid in the mycobacteria. So mycobacteria are sensitive to alcohol. Any question about that? So most of these things will be fairly resistant to alcohol, but the mycobacteria are not, even though to most other agents, the mycobacteria are very resistant to the microbial agent, but they're not resistant to alcohol. So they're just pointing out that the different characteristics of the different groups can give specific characteristics, specific differences. like alcohol is not good, will not do anything to a prion, and won't do anything to endospores, but it's very good at killing mycobacteria. Okay. Any question about any of that? All right. While microbial control methods are effective, especially the biocides, they are not uniformly effective against all microbes. The compounds discussed in this lecture are not generally useful in disease treatment, with the exception of the antibiotics. Any question about any of that? All right, that's it for chapter 7. There is no lab for today, so I'll only be in from 6:30 to 6:45 to answer questions, but after 6:45, assuming that there's no further questions, I will log off. If you don't have a question, you do not need to come in to the lab. And that's it for our lesson. Next Thursday, I'll be giving a review for the final. Any questions? All right. I will see you either in the lab or on Thursday. Bye.